Hello, my name's Will, and I'm going to be presenting today on algebra in the Islamic Golden Age. So just to give a quick overview of where we're going with this, we're going to start with a little bit of an intro, sort of get ourselves situated, when are we, where are we, and who are we looking at. Moving on to the historical context and sort of the social political situation of medieval Islamic world. And then looking first at Al-Khwarizmi and the origins of algebra, moving on a little bit to Omar Khayyam and some advances in algebra, and then touching a bit more on the transmission and legacy of medieval Islamic mathematical scholarship and how that influenced the Renaissance mathematicians and really how it laid the foundation for what we perceive today as modern mathematics. And then at the end, we'll just sort of recap everything and I'll share the homework assignment. So, when are we? We're looking at the 8th through 13th centuries AD. It's a span of about 600 years. And this is the period that's considered the Dark Ages in Europe. So, Europe is sort of not really intellectually flourishing. It's considered like a regression period. But at the same time, in the Islamic world, this is a time of flourishing. And it's sort of thanks to the growth of Islam and the spread of these caliphates. For context, Euclid was around about 300 BC, so right around 1,000 years before this. Some of the Indian mathematicians that we looked at, Aryabhata first, was around 475 AD, so like 300 years before this, and Brahmagupta around 600 AD. That was around 200 years before this. And then Descartes and Newton, some of the major Renaissance mathematicians, came around 300 years after this period. Just to give an idea of sort of what's the mathematical timeline we're working in. So where are we located? Well, the capital of the Abbasid Caliphate, which was the longest reigning caliphate, was in Baghdad, sort of modern-day Iraq, somewhere round about here. Very central. And I'll just skip around in this video a bit to show just the extent of the Islamic Empire. So starting in 622 with the foundation of Islam, jump around a bit, you can see the Umayyad Caliphate. Originally, it existed before Islam, but once the rulers of the Umayyad Caliphate adopted Islam, it spread Islamic culture and religion very, very far because the Umayyad Caliphate was so powerful. And you can see, getting out over here, touching into India, across all of northern Africa, up into Spain. It was really incredibly widespread. Look, going up further into like France, modern-day France. We now see the Abbasid Caliphate, again, stronghold in the Arabian Peninsula, going further in towards Asia, always still maintaining this sort of strong connection into North Africa, Europe, up into Spain and Sicily. And it really maintained this powerful and very widespread empire sort of throughout that entire period of the 8th through the 13th centuries until the fall of the Abbasid Caliphate around 1258. And that brings us to who are we looking at? Who are some of the key figures? So the main figurehead is for Islamic algebra in the medieval era is Al-Khwarizmi. He lived from around 780 to 850 AD, and he's considered the father of algebra. He established methods for solving linear and quadratic equations, and he is widely credited with spreading the Hindu-Arabic numeral system, or what we now know today is just Arabic numerals. As well as that sort of place value decimal numbering system, which is so convenient for calculations. Another major figure was Thabit ibn Qurra. a little bit later than Al-Khwarizmi, but a bit of overlap there from 836 to 901 AD. And he was primarily a translator of Greek texts. He made some contributions to number theory as well, but his biggest contribution was he was part of a huge wave of translators in the Abbasid Empire, and that was a way that they were gathering this ancient Greek and Egyptian and Mesopotamian knowledge and being able to preserve it and then expand on it, which is really what the Islamic Golden Age was about. Another major figure we'll be looking at is Omar Khayyam. We'll be looking at his method for solving cubic equations. He was much later in time. He was nearer to the fall of the Islamic Golden Age, around 1040 to 1123 AD. And then another figure, sort of active a little bit before Khayyam, was Al-Karaji, and he is credited with the translation, or the transition that is, from a highly geometric-based algebra, where all the problems are sort of based on thinking about real physical objects, into symbolic algebra and taking those first steps into like entirely theoretical math. Because even what we saw with the pure math of the ancient Greeks was that it was still founded, or was still based in sort of real geometric constructs, whereas Al-Karaji takes a step away from that and says, we can look at, x cubed is very clearly, we can represent that in 3 dimensions as a cube, but what does the next exponent mean? And this was what a lot of what Al-Karaji worked on was exponents. Looking at the historical context for Islamic algebra, we see that the Islamic Golden Age was a period of intellectual growth in many fields, so not just limited to mathematics. This also included areas like engineering, astronomy, philosophy, medicine, life sciences, natural sciences. This was a huge cultural movement during the time, and this was partially aided by largely aided by the House of Wisdom, founded in Baghdad in the early 9th century. So this was a major center for learning, scientific research, and also a huge center for translation. The translation of classical works into Arabic, so works from Greeks and Indian scholars, and as well as later translating Arabic works into Latin for distribution in Europe. And this was a period of largely stable, a very stable cultural and political environment due to the security granted by the empire against outside threats, as well as the unified culture and religion of Islam throughout such a wide area. And because the empire spread so vastly, these trade routes created both immense wealth to fund this research, as well as a transmission route for ideas. So they were able to bring in these ideas from China and India, as well as from Southern Europe and Northern Africa. To just get a little further look at this, we can take a look at a timeline here provided by the Met Museum. You can see around 661, 662, with the foundation of Islam in 622, the Umayyad Caliphate adopting Islam, and then you can see the transition to the Abbasid Caliphate, who overthrew them, and they maintained that empire and that stability, at least in part, throughout the entire Islamic Golden Age. Moving on, let's take a look at Al-Khwarizmi and the origins of algebra. So Al-Khwarizmi was born in Persia, and he lived from around 780 to 850 AD. and he worked at the House of Wisdom in Baghdad. He wrote his most famous work. I'll butcher the pronunciation if I try, but it's commonly abbreviated to Algebra, which is where we get the word algebra, and it roughly translates to completion or restoration. And this book was really the foundation of algebra because it introduced methods for solving linear and quadratic equations with arithmetic methods rather than geometric methods. Beyond his contributions to algebra, he also introduced Hindu-Arabic numerals and their place value decimal system, as well as making works on algorithms. And the word algorithm comes from his name, Al-Khwarizmi, which had widespread use nowadays in computer science. And we'll look now at Al-Khwarizmi's method for quadratics. So before we get into his method, I wanted to look at how he's, even though he's not using a geometric solution, I wanted to look at sort of like how they're thinking about these problems in the medieval Islamic world. It's still very much rooted in geometry, but despite the fact that they're not, or that Al-Khwarizmi was not using geometric methods. So they're picturing a situation like this. You have x squared, which is literally a square, your quantity px, which is a rectangle of width p and a height x, and then you have some quantity q, which would just be a square with an area of q. And because of this, because of the geometric interpretation, they would never look at a problem like x squared plus px plus q is equal to 0. Like this root finding problem that's so common in modern algebra, because it doesn't really make sense to think about adding things together to get 0. They would only be looking at problems where two quantities are equal to another. So problems would take the form of x squared plus px is q, or x squared is equal to px plus q, x squared plus q is equal to px. Just variations on this, but they would never look at this sort of root finding problem like we would look at today. Again, because this was still very much founded in geometry at the time of Al-Khwarizmi. So let's work through an example of Al-Khwarizmi's method for quadratics. So Al-Khwarizmi would state the problem in words as a square and 10 sides is equal to 39. Stating these problems symbolically, the way that we do today as x squared plus 10x is equal to 39, that would come later during the Islamic Golden Age with Al-Kharajhi. But that is, that's all to say, this is equivalent to x squared plus 10x is equal to 39. And the way that they're conceiving of this is, again, you have x squared, you have 10 times some quantity x, and you want to figure out what does x have to be so that these have the same area as this. So Al-Khwarizmi's method is take half the number of sides, so you would take, he considers this one side, and you have 10 sides, so you would take 5, square it, and you have 25, and add it to the number. So 39 plus 25 is equal to 64. And then you would take the root of 64, 8, and subtract half the number of sides. So you'd subtract 5 from 8, and you get 3. And 3 is your value for x. And while Al-Khwarizmi, gave this algorithm, or this method for solving this, the proof that he gives is a geometric proof. So the way that he works it is by completing the square, and that's really all this method is just completing the square. He takes his value for x, or his x squared, lines it up along the side with his 10 sides, splits that in half, and then we fill in this square here, and then we add 25 to both this quantity and the quantity 64. If we take the root of 64, we know that 5 plus x is going to be the same as the root of our square here. So we know that if we subtract 5 from each, we'll get our missing value x. And this is sort of what this is, this was Al-Khwarizmi's proof for his method, and this is, again, how he'd be conceiving it at the time. It's very much, these are physical quantities. And what's also important to note here is that Al-Khwarizmi would only be looking at the positive roots, right? There would never be a world in which he would have a negative number of sides. It doesn't really make sense geometrically. So moving along, we can take a look at Omar Khayyam's method for cubics. So Omar Khayyam came later, again about 200 years after the death of Al-Khwarizmi, and he's sort of best known for his work in cubics and for developing geometric solutions for cubic equations. And he showed that the cubic equations can't be solved using algebra alone, and in fact you need geometric constructions in order to solve them. And this sort of laid the groundwork for what we would consider today as to be algebraic geometry. So Khayyam would look at a problem like a cube and sides equal to a number. So a cube, a physical cube object, and a number of sides of that cube are equal to b, a number. Interpreting this geometrically, he would be conceptualizing this as x cubed. We can look at this image over here. X cubed, literally a cube with all sides length x. If we think about a and break it into its square root, so we have p squared, you can think about this as having depth x and then faces of height of p and then also a width of p. So this is sort of like p squared on the face times x depth. And then again, p squared on the face and a depth of q. And that's how he would represent this b. Because all of these objects would have to be of the same type, right? You have to be adding all volumes together, or in the case of Al-Khwarizmi, these were all areas, 2D areas. And a proposition that we'll use before getting into Khayyam's method is we will use this property that for a circle with diameter q, as given here, if we cut it at any point along that diameter and draw a line up to the perpendicular line up to the edge of the circle, we get this length y. This property states that the ratio x over y is the same as the ratio y over q minus x. And we'll use this proposition in showing Khayyam's method for cubics. So you'll have to forgive the handwritten notes here, but we're looking again at the problem x cubed plus ax is equal to b. We translate that to get it into sort of a geometric interpretation in terms of cubic volumes. We'll move our term p squared x onto the right-hand side, and then we'll factor out the p squared, and we'll factor x cubed as x squared times x. And then we'll cross divide to get two fractions here. And this is something that Khayyam would have understood more in terms of proportions. He would have understood this as a proportion in this way, but I think using modern algebra notation, it's a little bit easier to understand some of the divisions and multiplications that we're doing here. So we can translate this proportion into two fractions. X over y is equal to y over q minus x. If we manipulate that a little bit, we can get to this intermediate step, and then eventually to y squared plus x squared is equal to x cubed. So this is an offset circle. And in this case, this is a circle with q is equal to 4, diameter 4, and it's offset so that the center, or so that the left-hand edge is exactly the origin. And if we multiply both sides by y, and then divide both sides again by q minus x, we will get this term here. If we then plug in this identity that says q, or x over q minus x, is equal to p squared over x squared, we use that identity here, then we get that p squared over x squared is equal to y squared over q minus x squared. We take the square root of both sides, and then we use the identity, the original identity here, to get that p over x is equal to x over y. And then cross-multiplying these, we get py is equal to x squared. And this is the equation for a parabola. So what we're really looking at here is a system of equations that we have our first equation, y squared plus x squared is equal to xq, and py is equal to x squared, and we want to find the intersection of these. Today we can do that very easily using Desmos. You can see here an example of how this is graphed, and you would just find the intersection point here, and this would be your value for x. Now this is not exactly how Khayyam would have done it. Again, this is using a lot of modern algebraic techniques, but and you can see here, this is from Khayyam's text. His graph looks a little bit different from mine. It seems to be kind of intersecting maybe a different place, but you can still clearly see the method that he's using, a circle intersecting with a parabola. And again, we can do this easily in Desmos using Cartesian coordinates, but this is like 500 years before Descartes was born, so they wouldn't have been using this, but parabolas were actually a ruler and compass construction that was possible to do. So this certainly wouldn't be something that's out of their grasp, and obviously it wasn't, because they did it. So let's now look at Al-Khawarizmi and the shift to symbolic algebra. So Al-Khawarizmi lived from 953 to 1029 AD, a little bit before Al-Khawarizmi, and he lived in Baghdad and worked for the ruler of Baghdad. And he was very prolific in not only mathematics, but also engineering and hydrology. And sort of for the latter half of his career, he sort of put down mathematics to focus on engineering of wells and supplying water to the city. His most famous book is called Al-Fakhri, or again, I'll butcher that, but it translates to Glorious on Algebra. Humorously, he had two other books. One was called Wonderful on Arithmetic, and the other merely Sufficient on Arithmetic. But in Al-Fakhri, he defined monomials, x, x squared, x cubed, so on, and as well as their reciprocals, but without any reference to geometry. So he was taking it purely into the theoretical realm, away from these symbols referring to actual geometric objects. In addition to this, he laid some of the groundwork for proof by induction. He took it. He didn't do it in what we would consider, a mathematically rigorous way today. He would just sort of show the first 5 steps, the first 5 induction steps, not proving that it works in all cases. But certainly he had that idea for that proof by induction could be done. On the right here, we're looking at sort of a modern interpretation or a slightly modernization of how Islamic scholars would have written numbers in the latter periods of the Islamic Golden Age. So they referred to units as ahad, so this would be 110 ahad. Shay, or jitter, which just translates to thing, that is, and that's written with the modern English, or the modern letter T, and that would just refer to their x, or their side length. And then they use the word mal, and that referred to x squared. So this is how they would have written, essentially, x squared plus x is equal to 110. And again, they wouldn't have used m and t. They would have used, whatever the equivalent Arabic letters are. I don't believe they were using this exact equal sign. I think it was a little bit closer, like an L shape or an angle bracket. But this is sort of the idea of how they would have been writing these equations in the latter half, or not the latter half, but the latter period of the Islamic Golden Age. Let's look now at the transmission of algebra to Europe. So this was largely brought about by the translation of Arabic texts into Latin, which was the scholarly language in Europe at the time, and primarily in areas like southern Spain, Sicily, sort of Islamic strongholds in southern Europe. In particular, Toledo in Spain had the Toledo School of Translation, and they translated many important Arabic works into Latin. And that was across not just math, but also engineering and astronomy. A major contributor to this spread was Fibonacci. So he was around after any of the figures that we've looked at in 1170 to 1250 AD, right towards the end of the Islamic Golden Age. But as a young man, he studied in North Africa, across Egypt, Tunisia, all across North Africa in the Islamic world, and he studied specifically math and astronomy. And he wrote a book in 1202, Liber Abaci, which translates to the Book of the Abacus. And it was widely published in Europe, and it brought Al-Khwarizmi's methods for quadratics, as well as the Hindu-Arabic numeral system to Europe, and certainly other works by later Islamic mathematicians. And this transmission of algebra into Europe laid the groundwork for Renaissance mathematicians 400 years later, people like Descartes and Newton. And this information really was the foundation of what we consider modern mathematics. So to recap, we've looked at the Islamic Golden Age, which was a period of about 600 years with major intellectual flourishings across all sorts of fields, from engineering, medicine, and of course we've looked at mathematics. And we've looked at Al-Khwarizmi's methods for solving linear and quadratic equations. And we've spoken on how he's the father of algebra, and how he introduced Arabic numerals and popularized them, along with the place value number system. And we've also looked at later advances by Omar Khayyam in solving cubic equations. And then we also touched on Al-Karaji, who set the foundations for shifting away from geometry-based problems and toward abstract algebraic methods. And now he kind of laid the groundwork for all sorts of theoretical math that we think about today. And overall, we've looked at how the Islamic world preserved and expanded on ancient Greek and Indian mathematics, and was really the bridge from Euclid and Indian mathematics into Renaissance Europe, and built the foundation for pre-modern and modern mathematics. And let's now look at the homework. So we'll be using the methods that we showed earlier to solve the following equations. So x squared plus 6x is equal to 16, and x cubed plus 9x is equal to 54. When you use Al-Khwarizmi's method, I want you to draw the shapes on paper to show the geometric proof that Al-Khwarizmi used to show the relationships between the values. And then when using Khayyam's method, you should graph the circle. You should identify, P and Q, and then graph the circle and the parabola in Desmos and find the intersection, and that should be your solution for B. And then you'll turn in your solutions for A and B, so what's your x value for A, what's your x value for B, along with a screenshot from Desmos, and then a photo of the shapes from Al-Khwarizmi's method.